So we're going to look at how we can test the mean um, for hypothesis test for one sample. So we did when we looked at introducing hypothesis testing, we looked at the fact that Z was equal to X bar minus mean over the standard deviation of the square root of n. This is the population mean. This is the population standard deviation. And this works great if we know both these, well, if we have an idea of what this is that we're testing with, and if we know what this is. So this means we need to know sigma, the population standard deviation. What if we don't? What if we don't know what it is? If we don't know what that is, then what do we do? So if we don't know what that is, could we just use the standard deviation for the sample? We could. Usually the sample values actually do a good job of telling you what the population values are. So we could. But in that's the case, could we still use the same thing? Is this X bar minus the mean over S over the square root of n, is it still normal? And the answer is no. Unfortunately, it's not still a normal distribution. So we need to figure out what to do with that and how to go about doing this. So statisticians went, okay, this is not a normal distribution. Now what do we do? How do we figure out what it is? And then we got to figure out what to do with that. So this is what we want to kind of go into of how to do this and what this is and what this value is. And so that's what we want to do next, is try to figure out what to do. And statisticians kind of looked at that and said, well, what should we do and how do we go about doing this? And they went, a man by the name of W.S. Gossett came up with a theorem that talked about what it was. He did some research into it and looked into what it was. He created something called the student's t-distribution. Now, it is not called the student's t-distribution because students use it only. He called it that because he couldn't call it the Gossett t-distribution, which I'm sure he would much prefer to have done. He couldn't do that because the company he worked for didn't want people to know he worked for the company and who he was. And the reason I say that is he worked for a company that I'm sure you've never heard of called Guinness. And he worked for Guinness and he was making beer for them. And he was a chemist who was making beer for them. And if you don't know anything about making beer, when you're making beer, your beer has to be, you have to have the same ingredients in all places, including the water. It needs to be the same. Well, Guinness was getting larger into the point where they were starting to make their beer other places, and they wanted to be able to have the same taste in their beer no matter where they made it. And they needed, therefore, figure out how to make their water be the same wherever they made their beer. And W.S. Gossett was looking into this and researching this, and he found out he needed to do some testing that he couldn't do, and that's why he came up with the student's t-distribution, because he didn't know the population standard deviation. So the question was, what does he do? What should he do in that case? And so he then said, well, he came up with this theory, and Guinness didn't want their other competitors to know that they hired a chemist. So since Guinness didn't want their competitors to know they hired a chemist who was doing this work to make sure of this, they wouldn't let him publish under his own name. So he published under another name, and he used the name student as what he published under. So that's the theory of W.S. Gossett and where he came up with the student's t-distribution and why it's called student's t-distribution. And what he says is, if we assume that first off we have a random sample, so we always need a random sample of size n is taken. and the population of the random variable is normally distributed. If we assume both those things, then T equals X bar minus the mu over S over the square root of N is distributed as a student's T distribution with N minus 1 degrees of freedom. So now I need to explain what that means. What is this N minus 1 degrees of freedom, and where does it come from? So let's look at what that is. First off, I want to mention that S, again, is the sample standard deviation. The way it is calculated is using a formula that says S is equal to the square root of the sum of X minus X bar squared over N minus 1. Notice there's an N minus 1 down there. And that N minus 1 is the same as the N minus 1 up here in degrees of freedom. So I did want to mention that. But what this is meaning is that when I go to calculate this, the best way to calculate this is to take X and then take each of the X's and subtract the mean. So you take an X, subtract its mean, get a value. Do that again and again and again. And you can keep doing that to get all of your values done. There should be N values here. And there'll be therefore some values here. But the problem is that when you do that and you add up this column, this adds up to 0. This column must add up to 0 because this X bar is your center and you're looking at the change from that center. So you should get 0 here, which means, that, notice I didn't put 1 here, it means that this value here is predetermined. This must be figured out. This must be a certain number so that when all these add together, you're going to get 0. So this one's predetermined. So instead of being N values that are predetermined, or that are not predetermined, N values that are kind of have the freedom of being chosen for you, this last one's predetermined. So you actually have N minus 1 numbers to pick that get to be kind of found on their own. And so that being the case, you have 1 less degrees of freedom to do that. Another way to think of this is, let's say you have 5 people in a room and you have 5 chairs. The first person gets to pick from one of those 5 chairs. Doesn't matter which chair they can pick any one of those 5 chairs. Then, and they sit down. The next person doesn't have 5 chairs to pick from anymore. They now have 4 chairs to pick from because that first person sat down. So they only have 4 chairs to pick from, and they would sit down. Then third person only has 3 chairs to pick from. The second person has 2 chairs to pick from, and the last person doesn't get a choice. So that person doesn't have degrees of freedom to choose anything. They've lost it. They have to pick in that last chair that's there. So that's another way to think of degrees of freedom. And this degrees of freedom is actually the same as this N minus 1 degrees of freedom up here. That same kind of concept of why that is. So that's kind of what degrees of freedom is. It's just a technical idea. The student's T distribution looks a lot like a normal curve. So this is the graph of a degrees of freedom of 10 curve. This is a graph of degrees of freedom of 15. Notice the curve depends on your degrees of freedom. So as your degrees of freedom changes, your curve changes. Notice that as the degrees of freedom increases, you get more of a peaked looking curve than you did before. It is centered at 0, just to let you know. And it turns out if you look at this, it's going to keep increasing like this, and it's actually going to look a lot like a normal curve. So as your degrees of freedom increases, you're going to get closer and closer and closer to a normal curve. And that's all this says, is that as the degrees of freedom increases, the T distribution approaches the standard normal distribution. The standard normal distribution is the one that's centered at 0 with a standard deviation of 1. So now that we have that idea of this student's T distribution, we can talk about the hypothesis test for the mean, a one sample T test. As with everything, your first step of every hypothesis test is to state your random variable and your parameter. So this would be what you measured and what you are estimating. So in this case, you would have an X value here, and your X value would be your variable, whatever that variable was. And you can only pick on one of the variables. You might have more variables in your data set, but you're only going to have to look at one of them that will actually be based on the question you're asking. Then you're going to have the mean of that variable. That's your parameter. Remember, the parameters are numbers you're calculating from the population. So the symbol for mean is mu. You don't have to use the symbol. You can just use mean. I don't care. But that's your symbol you're working with. Once we have that, we can now state the hypotheses. Again, there's a null hypothesis and an alternative hypothesis. The alternative hypothesis is what your question is, what you're actually trying to answer and research about. So it's usually going to be your mean is not the same as some known value. You can also do your mean is less than some known value, or you can do the mean is greater than some known value. These days, we usually just do the not equal to, but I do want to mention the other two are there. Your HO, therefore, is always equal. Your HO always is an equal statement. You would also state your level of significance. And that's your alpha. Once you have that, you then go on to state and check your assumptions. So this is kind of nice because W.O. Gossett already did this for us. He already stated our assumptions for us. We just didn't notice it was stated that way. And the first assumption is we have a random sample of size n is taken. That was his first assumption. His first assumption was that you had a random sample. So that should be your first assumption here. And then what you do with this is you're going to check it. And that means you can describe how the sample was taken. And it should be you have a random sample. That shouldn't be a problem. You should already have that because you control how you take the sample. Your second assumption, if you look back at W.S. Gossett's theorem, was that the population of the variable is normally distributed. So that's your second assumption. And we check this using the normal density plot and the normal quantile plot. Remember, your normal density plot should look like a bell-shaped curve. Your normal quantile plot should look like a linear. Okay. The nice thing about the student's t-distribution is the student's t-distribution, I think it is this way, is actually fairly robust to this normal distribution idea if your sample size is large. So the student t-distribution is what we call robust, which means it works okay even if you don't have this assumption, as long as your sample size is large. So you probably should look first to see if you have a normally distributed population. And if you don't, then as you had a large enough sample, and we mean large, really we mean bigger than or equal to 30, but even bigger than that would be good. Then you can say that you have, that it's okay that it's not because it's robust to this idea. Once we get to that, you then get your calculations. On RStudio, you do a t-dot test. So this is called a t-test because it's using the student's t-distribution. So you do a t-dot test. Then you have that tilde as we've had before. You put in variable, whatever the variable name you're using. You then put a comma and you do mu equals whatever HO says. Not HO itself, but whatever HO says. So this should be whatever HO says. whatever HO says mu is equal to. Then you'd have your data equals your data set. And then you do either alternative equals less or alternative equals greater, depending on if you are your HA. And if you happen to be an HA of not equal, you just leave that off. So if your HA is mu not equal to some known value, then you leave off the alternative. Okay. That statement doesn't need to be there if you have, because R just assumes it's that way. Once you have that, we'll look at what the results are when we do an example, but you can pick out there from there your test statistic, your p-value, and your sample statistic. Then you get your conclusion and your interpretation. And these are still the same. You're going to reject HO if your p-value is less than alpha. And you're going to fail to reject HO if it's not. And then you'd have your same interpretations. There either is enough evidence to show HA or there's not. So let's go ahead and do an example of this. A major car manufacturer wants to test a new engine to determine whether it meets new air pollution standards. The mean emission of all engines of this type must be less than 20 parts per million of carbon. 10 engines are manufactured for testing purposes, and the emission level of each are determined. The data in parts per millions are listed below. So here's your data. I also happen to have it in to put into RStudio. And then at the 5% level of significance, do the data supply sufficient evidence to allow the manufacturer to conclude that this type of engine meets the pollution standards? So again, first step is to state the random variable and your parameter. So looking at this, I'm going to go back up here and see what did I measure. So one thing is I only have one one column in my data set, so that will be a little bit easier to help me figure that out. But these numbers are my emission levels. So this is what I measured was the emission level of the new engine, because I don't care about the other engines, I care about the new engine. Then I'm going to be looking at the mean emission levels. That's the parameter I'm going to be talking about. And I know that because it actually says, do we meet the standards? We're talking about numbers. So it looks like we even have the mean up here, the word mean up here. So I know that I'm having the mean. So mu equals the mean emission level of the new engine. Because again, I don't care about the old engines, I care about the new one. Now that I've done that, I can write my hypotheses. So I can state my hypotheses. We usually list HO first, but I usually do HA first. So HA is talking about the mean emission level of the new engines. And up here it says that they must be less than 20 parts per million. So we know it has to be less. So mu, the mean, has to be less than 20 parts per million. HO is always equal. So once you get what HA is, and this is my question, so I usually start with this, then I just put an equal sign instead of the inequality sign. The other thing I want to do is my level of significance. That's my alpha level. And it tells me right here that I'm supposed to use a 0.05 level. All right. Now that we've done that, let's go do the assumptions. So we're going to state and check assumptions. So first, you always want to state them first. So let's state them. We have a random sample. of, and I believe we had 10, so of 10 emission levels. So it's not 10 engines, it's the emission levels of the engines is taken. So that's my assumption. That's what's supposed to happen. Now the check is, did it happen? So let's go back real fast and look at this problem. And we see here it says 10 engines are manufactured for testing purposes. Well, that doesn't sound like a random sample to me. That sounds like they actually just made a bunch of problems, a bunch of engines. Now, in reality, that's probably what they're going to do, because they're not going to make a whole bunch and then randomly pick 10. They're going to make only the new ones and then test them. So in reality, this is probably what they would do, but it is not a random sample since they were chosen or manufactured. So that's not the best thing. So it's not a random sample since it was manufactured. Okay, so then our next step, our step 2, is to do the state and check of the other one. So the second one is that the population of the emission levels is normally distributed. Okay, well, that's our assumption again. That's what's supposed to happen. Now let's check it. Let's see if that is what happened. So we're going to go take our data. We're going to go put it into R. I'm going to go see what it is. Now this one's going to be a little bit different because I don't actually have the emission levels as a data set. This is just a variable we're going to type in. So this is going to be a little bit different than what we normally do. But the process is kind of this, is very similar. So let's go into RStudio. I'm going to put this data set into there. Again, this is not a data frame like we're normally used to. This is a different one. This is just a variable. Note it even comes down here in a slightly different place in your global environment. This is your emissions. You can click on it, but it's not going to do anything for you. It's not going to open it up because it's not really a data frame like these are. This is just a variable. But I still can do the things I've been doing with it. I can still create a graph function, density plot, of my emission and let's just see if that works. No, that doesn't work. So we're gonna have to do a slightly different. We're just gonna do density of emission. Nope. We'll do a histogram of emission. And there's my histogram. And that has a nice little bell shaped to it. So it looks like it's okay. It looks a little skewed, but it looks pretty good. So even though I couldn't do a density plot because I don't have actually a the normal thing we have, but we're close. We still can get that thing. And so we probably look like we are okay. So again, I'm going to copy this into my and put this into where I am. And this histogram, I didn't do a density plot because I don't have the right data set in there, but I did kind of the same idea. It looks kind of bell-shaped. So this looks like it's okay. The histogram looks okay. So this assumption has been met. Which is good because it wasn't a very big sample in the first place. So it's a good thing we have that. Okay. So now we can go to our calculations. And again, we're going to use R to do those. So I'm going to go back to my RStudio. This again is a little bit different. We have t.test. I'm not going to put the tilde in there because I don't actually have a data set here. I am going to say mu is equal to 20 because that's what HO says. And then I'm going to use alternative equals less, because if you look back at our HO was mu is equal to 20. So that's where that mu equals 20 thing. And then we are less than 20 parts per minute. So we're using alternative is less. So that's why I did that. And then I just hit enter. And there's my values. Again, this is slightly different than you would do. You don't have a data set here, but kind of the same idea works. So we'll go put this over here, and then we can talk about what all these things are. So here's our calculations. This is how I typed it in. Again, it's slightly different because I don't have a data frame, but it's basically the same idea. And so it tells me I did a one sample t-test, which this is because we only had one sample. Notice you can see that because there's only one sample here. So we have that information. We only had one sample. It tells me my data is emissions. That was my variable. So it's a good thing it told me that. It then tells me T is equal to negative 3.0016. That's my test statistic. So that's what Gossett was talking about. That's your test statistic. Your p-value is your p-value. Then it does tell me my alternative hypothesis is the true mean is less than 20. That is what HA was. So it's a good thing that said that. Don't worry about what this 95% confidence level is. And then tells you the mean of X is 17. So that's actually your X bar. So I can now write down that my test statistic is equal to T is equal to negative 3.0016. My p-value is equal to 0.007456. And my sample statistic is X bar is 17.17 parts per million. And so now we're at the step of conclusion. And because my p-value is less than alpha, my p-value is less than my alpha level, I'm going to reject HO. And then we can get to our interpretation. So that's your conclusion. That's all you have to say for your conclusion. Now my interpretation is there is enough evidence to support that the mean, and I don't want to just say HA because I want to say what HA says. This is your reader is going to want to read this. They're not going to want to read your whole thing to find out what stuff is. They want to read what the conclusion is. And so there's enough evidence to support that the mean emission level for the new engine is less than 20 parts per million. And great, so we have enough evidence for that, we're good, and it's all ready to go. So that's your final step, and that is the end of our hypothesis test for one sample t-test.